Okay, good morning. Bit of a late start this morning, but we're going to dive right in anyway, because that's what we always do. Welcome to my stream. And let's take a look at where we left off yesterday with crafting interpreters. So we finished chapter 22. We did that all in one day. We also we started and finished chapter 22, but we also finished off chapter 21. So it was a pretty straightforward, I guess, stream yesterday. We didn't have too many difficulties. Yeah, so we did assignment, and then we did all of chapter 22, which is local variables. And now we're going to look at jumping back and forth, which is about control flow. So let's dive right in, as I like to say. It's taken a while to get here, but we're finally ready to add control flow to our virtual machine. In the TreeWalk interpreter we built for JLocks, we implemented locks' control flow in terms of Java's. To execute a locks if statement, we used a Java if statement to run the chosen branch. That works, but isn't entirely satisfying. By what magic does the JVM itself, or native CPU, implement if statements? Now that we have our bytecode VM to hack on, we can answer that. When we talk about control flow, what are we referring to? By flow, we mean the way execution moves through the text of a program, almost like there is a little robot inside the computer wandering through our code, executing bits here and there. Flow is the path that the robot takes, and by controlling the robot, we drive which pieces of code it executes. In JLocks, the robot's locus of attention, the current bit of code, was implicit based on which AST nodes were stored in various Java variables and what Java code we were in the middle of running. In CLocks, it's much more explicit. The VM's IP field stores the address of the current bytecode instruction. That is right here. The value of that field is exactly where we are in the program. Execution proceeds normally by incrementing the IP, but we can mutate that variable however we want to. In order to implement control flow, all that's necessary is to change the IP in more interesting ways. The simplest control flow construct is an if statement with no else clause. If condition, print condition was truthy. The VM evaluates the bytecode for the condition expression. If the result is truthy, then it continues along and executes the print statement in the body. The interesting case is when the condition is falsy. When that happens, execution skips over the then branch, that should probably be highlighted in some way, and proceeds to the next statement. To skip over a chunk of code, we simply set the IP field to the address of the bytecode instruction following that code. To conditionally skip over some code, we need an instruction that looks at the value on the top of the stack. If it is falsy, it adds a given offset to the IP to jump over a range of instructions. It can be an offset, right? Or it could be an absolute location. Like if you're writing machine code, some branch instructions can be offset from the current IP, and some branch instructions can be absolute. So it's a choice. Otherwise, it does nothing and lets execution proceed to the next instruction as usual. When we compile the bytecode, the explicit nested block structure of the code evaporates. Right, because we only have a flat series of leaving only a flat series of instructions behind. Locks is a structured programming language, but CLocks bytecode isn't. The right, or wrong depending on how you look at it, set of bytecode instructions could jump into the middle of a block or from one scope into another. The VM will happily execute that, even if the result leaves the stack in an unknown inconsistent state. So even though the bytecode is unstructured, we'll take care to ensure our compiler only generates clean code that maintains the same structure and nesting that locks itself does. Okay. This is exactly how real CPUs behave. Even though we might program them using higher level languages that mandate structured control flow, the compiler lowers that down to raw jumps. At the bottom, it turns out goto is the only real control flow. Anyway, I didn't mean to get all philosophical. The important bit is that if we have that one conditional jump instruction, that's enough to implement locks' if statement, as long as it doesn't have an else clause. So let's go ahead and get started with that. If statements. Okay, this many chapters in, you know the drill. Any new feature starts in the front end and works its way through the pipeline. An if statement is a statement, so that's where we hook it into the parser. So let's pull up the compiler code and start working on if statements. So statement. So currently we have a check for print and a check for a left brace, which is a block. So right in here, we're going to check to see if it's an if with a capital I. And if it is, then we're going to call self-if statement. When we see an if keyword, we hand off compilation to this function. There it is. Okay. I'm just following this thing here. I know it doesn't matter in Rust, but I'm just following along anyway. Recommending where to put it. If statement. Because that way I don't have to think about where to put it. So consume the open paren. And we have an expression. We consume the close paren. And then we have this emit jump thing, which is new. Expect to open paren after if, self expression, and then self consume, token type, write paren, expect write paren after condition. And then we're going to say let then jump is equal to self emit jump opcode, and we're going to add a new opcode here, jump if false. And then we're going to say statement, and then we're going to call another new function here, apparently, touch jump, then jump. Huh. Okay. That's interesting. So let's just read a little bit here. Have you ever noticed the open paren after the if keyword doesn't actually do anything useful? Language would be just as unambiguous and easy to parse without it. Like if condition close paren, print looks weird. The closing paren is useful because it separates the condition expression from the body. Some languages use the then keyword instead, but the opening open paren doesn't do anything. It's just there because unmatched parentheses look bad to us humans. Yeah, and in Rust we don't even have that, right? We use everything has a brace. So that just turns into an open curly brace. That way we don't have to have the open paren on the if in Rust, because we have the open brace to tell us when the condition ends. Right? Easy enough. First we compile the condition expression bracketed by parentheses. At runtime, this will leave the condition value on top of the stack. We'll use that to determine whether to execute the then branch or skip it. Then we emit a new jump if false instruction. It has an operand for how much to offset the IP, how many bytes of code to skip. If the condition is falsy, it adjusts the IP by that amount, something like this. So we have condition expression, op jump if false, then branch statement, and then continue. So if the condition is false, we jump over the then branch. The boxes with the torn edges here represent the blob of bytecode generated by compiling some subclause of a control flow construct. So the condition expression box is all of the instructions emitted when we compile that expression. Right. But we have a problem. When we're writing the op jump if false instructions operand, how do we know how far to jump? We haven't compiled the then branch yet, so we don't know how much bytecode it contains. Entice, thank you for the follow. To fix that, we use a classic trick called back patching. We emit the jump instruction first with a placeholder offset operand. We keep track of where that half-finished instruction is. Next, we compile the then body. Once that's done, we know how far to jump. So we go back and replace that placeholder offset with a real one, and now that we can calculate it, sort of like sewing a patch into the existing fabric of the compiled code. So we have opconst 31, op jump if false, and then we patch in the 4270, and then apparently there's an op pop. I need a pop filter for my mic, I think. We encode this trick into two helper functions. We have emit jump and patch jump. I see it down here. So emit jump is we emit a byte of instruction, which is what we just passed in. Right? We emit 2 bytes of 255, sorry, and then return current chunk count -2. Current chunk count -2. Huh. Okay, let's think about this before we write any code. We do have a chunk. Count. The only count we have is here, chunk. So what do we have available to us in the chunk? We have the IP, which is the offset. When we emit a byte, oh, okay. When we emit a byte, fn emit, we write into the chunk, and then apparently we're going to need the count of how many. Right. We're going to how big is the array, and we're going to set it to -2 to the start of these 2 bytes here. So does our chunk have a? It has a write, a read, a get line, add constant, get constant, a disassemble. And that's it. We don't have a way of getting at the count. So we can just add a function called count. Right? We can just do that. Let's throw it in here. fpub fun count self. And all it's going to return is a usize. And it's going to return the size of the... It's doing an int, but Rust likes usizes for indices. So all this is the length of the lines. Self lines. Right, that's easy enough. And then back here, after emit bytes, we're going to put emit jump, self instruction, which is going to be an opcode. And it returns a usize. We did, okay, what do we save? Well, we're saving it right here, and then we just passed it in there. Okay, so it doesn't matter. I was thinking maybe it has to be U8s or something like that, but no, it can be whatever we want right now. So we'll do self emit byte of instruction into. Then we're going to emit 2 bytes of OXFF, and then we're going to return self chunk count -2, just like that. And then we still need patch jump, so I can't compile it yet. The first emits the first function emits a bytecode instruction and writes a placeholder operand for the jump offset. We pass in the opcode as an argument because later we'll have 2 different instructions that use this helper. We use 2 bytes for the jump offset operand. A 16-bit offset lets us jump over 65,535 bytes of code, which should be plenty for our needs. Some instruction sets have a separate long jump instructions that take larger operands for when you need to jump a greater distance. I remember the 6502 had branch instructions which could go like 127 in either direction, or 128 negative and 127 positive. And if you had to jump longer than that, you had to come up with a better way of doing it. The function returns the offset of the emitted instruction in the chunk. After compiling the then branch, we want to take that offset and pass it to this. I was saying do this after emit constant. Okay. Patch jump. Self. And offset is going to be the usize that we got from the chunk. -2 to adjust for the bytecode for the jump offset itself. So we already... Oh, this is where we're jumping to. Okay, and then the offset. We already subtracted 2 back here, but we have to subtract 2 again here. Let jump equal to self chunk count minus offset -2. If jump is greater than, was it U16 max? Is it like that? Rust U16 U18 max. Yeah. Standard U16 max. U16 might be already in there. Let's find out. When I try to compile, it'll tell me, and I'll put the standard in front of it if necessary. Self error. Too much code to jump over. I don't know how to test that. Self current chunk. Oh, we need to be able to write to a direct write at offset jump shifted by 8 and XFF, right? And then self chunk write at offset +1 jump and XFF. And I probably have to as usize it, or if I make it a usize, I could do it that way. Not a usize, sorry, U8 as U8, like that. As U8, like that. And then we're going to have to write a write at. We take that offset and pass it into this. This goes back into the bytecode and replaces the operand at the given location with the calculated jump offset. We call patch jump right before we emit the next instruction that we want the jump to land on. So it uses the current bytecode count to determine how far to jump. In the case of an if statement, that means right after we compile the then branch and before we compile the next statement. All right, so I'm going to create a write at, put right after write. At mod self, offset u size byte u8, like that, and all I'm going to do is self code offset Do we have to do anything with lines? Maybe not. Oh, because it's already been set up. Equals byte. That's all we have to do for that. Now the only thing I think we're missing is this opcode. So let's try to compile this and see if that's the only error. Nope, we have to standard. Oh, as usize. Was that the error before and I just threw a standard in there without thinking? Yeah. Okay. So that's the only error we have, is we don't have this opcode, which is what we're going to do next. We call patch jump right before we emit the next instruction that we want the jump to land on, so it uses the current bytecode count to determine how far to jump. In the case of an if statement, that means right after we compile the then branch and before we compile the next statement. That's all we need at compile time. Let's define the new instruction. Okay, so that's in chunk. And that is if jump, if false. Done. Over in the VM, we get it working like so. Oh, before I do that, let's put it here. Like that. And in VM, op code jump false. We're going to read short, so we don't have that yet. We do have read byte, so I guess we can just make it up. Let offset equals self read short, and we can just return the value we need, and then self if is falsy peak 0 vm dot ip plus equals offset. So we're still using the if in C or in Rust, so we can say if self dot peak 0 dot is falsy. Did I write is falsy or is truthy? I can't remember now. vm dot ip plus equals offset. That's it. That's all we need to do. We do need to write read short, and that's here. So we can say read short, read byte. Read short itself. It's going to be a U size. because we're going to end up adding it to the VM's IP, which is a usize. And so this is VM IP plus equals 2, and then we're going to... Oh, I see. He did it this way because we want to put it all into the macro. And he's using the comma operator in C to make this into 2 statements. The way C works is, you see the open paren and close paren here. That means this is an expression. This expression is divided into 2 sub-expressions using the comma operator. The comma operator executes the expression before it, executes the expression after it, and then returns, quote unquote. The result of the expression is the value of the expression after the comma operator. So it's similar to a semicolon, except you can have expressions instead of statements. We don't need to do that here because we're just writing a function. So we could say a self IP plus equals 2, and then we can return as usize oh, he's also cheating here, right? VM IP minus 2, VM IP of minus 1. We need to get this instead. So we're going to say self chunk read self IP minus 2 shifted by 8, or self chunk read self.ip minus 1, and we're going to cast the whole thing as a usize. Right. In his version, IP is actually a pointer, a byte pointer, a character pointer into the array of code, and so we have to do it this way. All right, what did I break? Closing delimiter. I missed a closing right here. Oh, self.ip. Is that the only error? We still should have, yeah, we have to disassemble it. Okay, and this is, so read short, that's read short. It yanks the next 2 bytes from the chunks and builds a 16-bit unsigned integer out of them. As usual, we clean up our macro when we're done with it. Okay, whatever. After reading the offset, we check the condition value on top of the stack. That's what we're doing here. Okay, he's describing this function here. If it's falsy, we apply this jump offset to the IP. Otherwise, we leave the IP alone, and execution will automatically proceed to the next instruction following the jump instruction. Oh yeah, right here. I said we wouldn't use C's if statement to implement locks' control flow, but we do use one here to determine whether or not to offset the instruction pointer. But we aren't really using C for control flow. If we wanted to, we could do the same thing purely arithmetically. Let's assume we have a function falsy that takes a locks value and returns 1 if it's falsy or 0 otherwise. Then we can implement the jump instruction like this. The falsy function would probably use some control flow to handle the different value types, but that's an implementation detail of that function. It doesn't affect how our VM does its own control flow. All right, this is the hand-wavy part. In the case where the condition is falsy, we don't need to do any other work. We've offset the IP, so when the outer instruction dispatch loop turns again, it will pick up execution at that new instruction, past all of the code in the then branch. Note that the jump instruction doesn't pop the condition value off the stack. So we aren't totally done here, since this leaves an extra value floating around on the stack. We'll clean that up soon. Ignoring that for the moment, we do have a working if statement in locks now with only one little instruction required to support it at runtime in the VM. We still need the disassembly thing. I guess he's saving that for later. I'm going to scan forward real quick and then we'll come back. Here it is. Oh, because he's going to do both. So he has another jump instruction which we haven't got to yet. And so there's only, okay, I'm gonna write this now and then we'll come back and do it for jump. I just want to get it to compile and then push, commit the change. Jump if false is going to be self jump instruction op jump if false. And the 1, this is passing in a sign. Okay, maybe that's going to, oops, didn't mean to do that. That's going to be something different later. We don't need to pass in the chunk, but we do need to pass in the offset. And then we're going to dump this out. Name is stir. We have sign, which is just going to be an int. I don't know, U8 maybe. And then it might be just a Boolean, right? C doesn't have, well, original version of C doesn't have bools, so this might be a Boolean. We'll have to change, I'll take a look at it later. Remember to come back and revisit that. Offset is just going to be usize, and it's going to return usize. The jump is going to be, see what he's doing is casting that as a U16 and taking the offset +1 and shifting it 8. And then ORing in that. So it's essentially kind of the same thing we did when we did the jump. So let's just use that same logic that we used in read short. Boom. And instead of using self chunk read, we can just do self code. And this becomes offset -1. We don't need that extra brace. And then this is OR self code offset. Oh, it's +1 and +2. Right. Offset +2, close. Right, we just need that, and we don't actually need this here. Okay, is that cleaned? That's clean. Okay, so that's the jump, and then we're going to say println. We're going to do the name like we do before, name -16, and then this is going to be jump, no, offset. Right, I'm looking at this here. Name, offset, offset +3 + sign times jump. Oh, I see. That's what sign is. So it's not a UA. It's going to be. Let's make it a. Ooh, so we're going to need negatives. Right. So let's make this an I16, just to match what they're doing as I16. There. Offset is going to be 4. And then an arrow. And this is just going to be this calculation that we have, which is offset +3 plus sign times jump. That way we can do negative jumps. And then we're going to return offset +3. No, we get 2 errors. I can't multiply sign by jump. Oh, expected usize, because offset is usize. How are we going to do this? Because offset is usize. This is doing a uint 8, right? Casting it as uint 8, and then it's saying multiply sign by jump. How does C handle this, right? Because it's going to cast that down to a int 16t. That's interesting. Here in Rust, we have a slightly more difficulty going on here because this offsets a usize, but we want to be able to subtract jump from the offset. So I guess what we can just do is let jump 2, sure, equals if sign equals 1, offset, it gives you offset plus 3 plus jump. No, we'll do it this way. If sign is 1, offset plus 3 plus jump. Else, it's going to be offset plus 3 minus jump. And then we'll just put jump 2. Like that. Nope. Expected use size find I16. Okay, so this we need to do. Oh, right, I did it this way. Okay. So this doesn't matter anymore. Yeah, let's leave it as I16. This can be use size. Right? Which it is not as use size. There. All right, that's a little trickier than here, because in C you get away with this kind of business, multiplying a signed integer by an unsigned integer, and have to worry about that. So here we don't have to worry about it, except this could end up going negative, right? And if this ends up going negative, jump 2 is unsigned. Jump 2 is a use size, sorry. So Rust will panic, but that means it's a bug in our code. Matt Blue, thank you for the follow. 9 more to get to 400 followers. Pretty good. Right, so there we go. So that's that jump instruction. But now we have to scan all the way back here. I think we have everything done in terms of this. Oops. There's jump to shift left by 8 I32, which would overflow. That's true. What we need to do is cast this first. Oh, right, and we don't need the return statement. Okay, so I think what I'll do is let me make a helper function. So we only have to do this in one spot. Where is it? So I'm gonna write a helper function here, I guess. Pub fun get jump offset self and then offset use size, and then all this is going to do is return this value here, but we're going to do all the casting so we don't have to worry about it. So this is as use size over there, and then that gets as use size, and then we can just say get jump offset. Oops. Assess the return to use size. There we go. And then this just says self get jump offset of offset plus 1. Right? Because that's what we had before. And then the other one is in the VM. Here it is. So we can say self chunk get jump offset of self IP minus 2. And that's already a use size. And then what was the other error or mistake? In the compiler we have line 227. We don't need that. Okay. Oh, now we have 4 errors. It doesn't like not interpreted as a shift, not interpreted as generic arguments. Weird. How did that even... Oh, because I had this here. Oh, I do want it around the whole thing, so I can as use size the whole thing. Actually, oops, I have a semicolon there. Nobody told me. All right, this might do as use size because we start off with use size, and it might promote this to a use size. Let's find out. Nope, as use size. There, 2 warnings, extra parens, right? Okay, so that's good. And what does Clippy say? Clippy's happy. So I should be able, we haven't gotten to else clauses yet. We just finished this part here. Right, we talked about the fact that it doesn't pop the condition off the stack. But can we do a run now? Cargo run. If 1 equals 2, print yes. All right, nothing got printed, but it did compile. Let's see if it compiled correctly. We have a constant 1, we have constant 2, we have check for quality. We have a jump if false to line 11. And line 11 is just return. And this prints out yes. And we don't have else yet. So okay, now let's check 1 equals 1. Print yes. And it printed yes. So we have, yeah. So this one executed 0, 2, 4, 5, and 11. And this executed 0, 2, 4, 5, 8, 10, which was the print, and then 11. So that's pretty cool. So I think if statements are working. We don't have else statements, but we do have if statements. Get status. Oh, that's right. The other thing, I have this object thing, which we're not using. RM. Yeah. Git commit -m section 23.1.0, right? 23.1. We didn't do all of 23.1. We did 23.1.0 if statements. And now we'll do 23.1.1 else clauses. An if statement without support for else clauses is like Morticia Adams without Gomez. Okay. So after we compile the then branch, we look for an else keyword. If we find one, we compile the else branch. All right. All right, so we patch the jump, and then we say if self is match token type else, then self statement. But we need to patch around this, right? When the condition is falsy, we'll jump over the then branch. If there's an else branch, the IP will land right at the beginning of its code. But that's not enough, though. Here's the flow that leads to. Condition expression, op jump if else, then branch statement, falls through, frowny face. Else branch statement, continue. Yeah, so we need a way to jump out. After the end of the then branch, we have to jump out. If the condition is truthy, we execute the then branch like we want, but after that, execution rolls right on through to the else branch. Oops. When the condition is true, after we run the then branch, we need to jump over the else branch. That way, in either case, we only execute a single branch, like this. So we have op jump, right? We need to implement that, we need another jump from the end of the then branch. Okay. So let else jump equals self emit jump op code jump. And this is an unconditional jump. And patch jump the then jump. If we match the token else, we do the token the else statement, and then we patch jump else jump. After executing the then branch, this jumps to the next statement after the else branch. Unlike the other jump, this jump is unconditional. We always take it. So we need another instruction that expresses that. I mean, you could theoretically emit nil or emit push nil and then jump if false, and then that would be an unconditional jump. So you wouldn't need this extra thing. We just need an extra tick of the clock in our VM, I guess. But that's fine. Op jump. In chunk, we add op jump. And down here, we add the opposite version of it. Op code jump. And then in VM, opcode jump. And that gets interpreted as let offset equals self read short. VM self.ip plus equals offset. And done. Now I'm thinking, oh yeah, so this is uint 16. That's fine. We don't have a backwards jump yet. We're always jumping forwards. So, but at some point we're going to have to be able to jump backwards, right? Otherwise you can't do loops. Nothing too surprising here. The only difference is that it doesn't check a condition and always applies the offset. We do need the disassembly. So let's throw that here. Opcode jump if just jump. And that's just a jump instruction. And I think it's just like this if I'm remembering correctly, and we leave sign alone. Yeah, so we're coming up to a negative jump at some point because we have a positive jump there. And I'm going to change that to a Boolean if that's the case. Because all we're doing is doing this if signed is 1. Actually, I'm going to do it now. Why wait? Forward. Bool. Forward. I guess I'll call it forward jump. And then these become true. Like that. Right? Does that all check? It does. Good. Let's just double check that this code works. Okay, and if 1 equals 2, print yes, else print no. And I printed no. Look at that. This is the code that got emitted here. Oh, we still have something on the stack. We haven't dealt with that yet. If I say print hi, we'll see the stack now has true and false on it. Because I guess at some point we're gonna have to pop these guys off, but yeah. So we have this. So if they're equal, we jump if we check to see if they're equal. We jump if false to 14, which prints out no. Otherwise, we'll push yes onto the stack, we'll print it, and then we'll jump to 17, which is our return statement. Very nice. Okay, Clippy. All right, is that the end of this section? Oh, here's the pops. Okay. We have then and else branches working now, so we're close. The last bit is to clean up that condition value we left on the stack. Remember, each statement is required to have 0 stack effect. After the statement is finished executing, the stack should be as tall as it was before. We could have the op jump if false instruction pop the condition itself, but soon we'll use that same instruction for the logical operators where we don't want the condition popped. Instead, we'll have the compiler emit a couple of explicit op-pop instructions when compiling an if statement. We need to take care that every execution path through the generated code pops the condition. When the condition is truthy, we pop it right before the code inside the then branch. Okay. So then jump. So just before this, we pop self emit byte opcode pop. Like that. Otherwise, we pop it at the beginning of the else branch. Here? I'll patch jump right after it. There. Okay. This little instruction here also means that every if statement has an implicit else branch, even if the user didn't write an else clause. In the case where they left it off, all the branch does is discard the condition value. The full correct flow looks like this. Condition expression, op jump if false, op pop, the then branch statement. Op jump, op pop, else branch statement. Yeah, so you could make this jump and pop like he said before, but we're going to reuse that instruction apparently. If you trace through, you can see that it always executes a single branch and ensures the condition is popped first. All that remains is a little disassembler support, which we already added. All right, so now that all checks. I mean, all we did was add those 2 lines of code. Cargo run. Let's do this thing here and see the pop instructions now. If it's equal, jump if false, and then we do the pop. There's the constant yes, print, jump, pop. And the way we executed was constant 1, constant 2. Are they equal? No, they're not equal. Jump if false, false, and we pop. Push the constant, print the constant, and return. Okay, so that's working. I guess we could check the other direction too, right? If 1 equals 1. And make sure the stack is empty. And the stack is indeed empty, and here's the pop instruction being executed on line 8 instead of on line 15 this time. Perfect. Section 23.1.1 else clauses. Nice. Okay, now we're up to logical operators. Okay. You probably remember this from JLock. Oops, did I miss something? All right. Oh yeah, this is just the disassembly, right? These 2 instructions have a new format, the 16-bit operand, so we add a new utility function to disassemble them. Right, we worked our way through that. There we go. That's one complete control flow construct. If this were an 80s movie, the montage music would kick in, and the rest of the control flow syntax would take care of itself. Unless the 80s are long over, so we'll have to grind it out ourselves. My enduring love of Depeche Mode notwithstanding. Logical operators. You probably remember this from JLocks, but the logical operators and or aren't just another pair of binary operators like plus and minus. Because they short circuit and may not evaluate the right operand depending on the value of the left one, they work more like control flow expressions. They're basically a little variation on an if statement with an else clause. The easiest way to explain them is just to show you the compiler code and the control flow it produces in the resulting bytecode. Starting with AND, we hook it into the expression parsing table here. I guess we can just throw it at the end of the rules here. Rules, token, type, and as usize. And we're going to do this as infix. Why is there an underscore after the and? I mean, we need it too, right? Because, oh, no, we don't. Or, neither one of those are keywords. Can we get away without it? Without the underscore? I wonder if there is... No, I don't think that's a reason. It might be a reserved keyword, although that's not used in C. Maybe C11 has it. No. I mean, that would be the only reason I would think that you'd put the underscore there to avoid it being a reserved, using a reserved word. But I don't think it is. I don't think it is. All right, I'm gonna try to get away without it and see what happens. Oh, and the precedence has to change. Precedence is equal to precedence and. I guess that's good enough. That hands off to a new parser function. So after defined variable, we're going to write a function called and it's going to take the can assign which it doesn't use. And it doesn't return anything. And now we're doing this jump stuff. Okay, so let end jump equals self emit jump op code jump if false self emit byte op code op pop, there we go, into self parse precedence and then patch jump end jump. Okay. At the point this is called, the left-hand side expression has already been compiled. That means at runtime its value will be on the top of the stack. If that value is falsy, then we know the entire AND must be false. So we skip to the right operand and leave the left-hand side value as the result of the entire expression. Otherwise, we discard the left-hand value and evaluate the right operand, which becomes the result of the whole AND expression. These 4 lines of code right there produce exactly that. The flow looks like this. Left operand expression, then we call AND, which pushes op jump if false, pushes an op pop. It does the right hand using the AND precedence, and then we patch the jump after the right operand expression. Now you can see why op jump if false leaves the value on the top of the stack. When the left-hand side of the AND is falsy, the value sticks around to become the result of the entire expression. We got plenty of space left in our opcode range, so we could have separate instructions for conditional jumps that implicitly pop and those that don't, I suppose, but I'm trying to keep things minimal for the book. In your bytecode VM, it's worth exploring, adding more specialized instructions and seeing how they affect performance. All right, so that was logical AND. We didn't need any new instructions for that, and it all just compiles. Should I commit this? Let's do this. Why not? Section 23.2.0 and logical AND. There we go. So the logical OR operator is a little more complex. First, we add it to the parse table. And so we're going to do the same thing we did here, but this is going to be OR. And instead of AND, this will be OR, and this will be precedence OR. When that parser consumes an infix OR token, it calls this. For some reason, this is after number instead of we don't need the can assign. All right, so else jump is emit jump pop if op jump if false. End jump is emit jump op jump. And we're going to patch the else, emit a pop, parse the precedence for the other side of the OR statement, and then patch to the end. Okay. Let me see if we can understand that. Else jump. All right, so this is jump if false followed immediately by another jump. Oh, I see, jump if false, and so it jumps around the jump. Okay, I think I'm following. Self, patch, jump, else, jump. So the else jump if false comes to here, and the true says, okay, go somewhere else to see what else needs to happen. Self emit byte, opcode, pop. And then self parse precedence OR, and then we patch in the end jump. Okay, I think I get it. In an OR expression, if the left-hand side is truthy, then we skip over the right operand. Right, we jump to the end. We say, okay, it's all done. Simon B says, what does : mean in Rust? Is it like object property? Hi, by the way. Yeah, hi. How are you? Welcome to the stream. Thank you for joining. The : is separating the name of the enum from the values within the enum. So you can see I've created an enum called precedence, and each one has, it's got a bunch of different precedences in there, precedence term. So it's just referring to that particular enum. If I look here, we have opcode pop, for example. And if I look in my chunk, we can see all my pub enum opcodes, : pop. So that's all that's doing. So it's typing. Yeah, it's typing. Exactly. Exactly right. Okay. So we need to jump when the value is truthy, right? So in order to jump when the value is truthy, you have to jump around the jump if it's falsy and then do the actual jump. We could add a separate instruction, but just to show how our compiler is free to map the language's semantics to whatever instruction sequence it wants, I implemented it in terms of the jump instructions we already have, right? And in fact, op jump could also be implemented in terms of jump if false with a push nil, like I was saying earlier. Okay. When the left-hand side is falsy, it does a tiny jump over the next statement. And that statement is an unconditional jump over the code for the right operand. Right? So that's going this, then it's going that. This little dance effectively does a jump when the value is truthy. The flow looks like this. And then we have to do the pop because we want to pop off that. If I'm honest with you, this isn't the best way to do this. There are more instructions to dispatch and more overhead. There's no good reason why or should be slower than and, but it's kind of fun to see that it's possible to implement both operators without adding new instructions, any new instructions. Forgive me my indulgences. Okay, those are the three branching constructs in locks. By that, I mean these are the control flow features that only jump forward over code. Other languages often have some kind of multi-way branching statement like switch and maybe a conditional expression like $:, but locks keeps it simple. All right, so that means if this compiles, it does, I should be able to cargo run and say if 1 equals 2 or 3 equals 4, print bad, right? And this, okay, and this is the or, disassembled. So we have a 1 and 2, we check to see if they're equal. We jump if they're false to 11. 11 goes down to the pop, which pops the false case off and then tries the next one. If it's true, then we jump to 17 saying we don't need, oh, interesting. We should be able to jump to here instead to do the pop. But this is checking it false again, which it just checked, right? So there's a little optimization here we should be able to make. That this jump here should be able to pop down to here. Let's take a look at and. 1 equals 2 and 3 equals, let's say 3 equals 3, print bad, right? Because that should also be false. So here we do jump if false to 14, which text jump if false again. Interesting. Did I do it wrong or no? There's no add 1. I wonder if this should be in the opposite order. No, you can't do that there. Huh. Okay, that's unfortunate. That's unfortunate. There's an optimization we can make there. Right? Jump if false is jumping to a jump if false. We could just go to the next instruction. Okay. But anyway, it's working. And that's good enough. Git commit -m section 23.2.1. Is it? Logical or operator. I forgot to check in with Clippy, but I don't think Clippy's going to complain. Yeah. All right, so let's get to while statements. Okay, so now we got looping. And it takes us to the looping statements, which jump backwards so that the code can be executed more than once. Locks only has 2 loop constructs, while and for. A while loop is much simpler, so we'll start there. And I might not be able to get to the for loop depending on how much time while statements take. Okay, we'll start the party there. In statement, we'll put it right here. If self is match, token type, while. Self while statement. Just like that. Okay. When we reach a while token, we call while statement. So this is going to be after print statement. I don't know why after print statement, but that's where it goes. While statement, not self. Okay, so we're going to start by consuming a left paren. We will do the expression, and then we're going to consume a right paren. Like that. Then we have our jump, exit jump. There we go. We emit the byte for popping. And then we execute a statement, which is going to be basically the body of the while loop. We patch in, exit, patch jump. And then we emit the final pop. Okay. I think that's it. Most of this mirrors if statements. We compile the condition expression surrounded by mandatory parentheses. That's followed by a jump instruction that skips over the subsequent body statement if the condition is falsy. We patch the jump after compiling the body, right, and take care to pop the condition value from the stack on either path. The only difference from an if statement is the loop. That looks like this. Emit loop. Ooh, really starting to second guess my decision to use the same jump instructions for the logical operators. All right, that's fine. So right here we say self emit loop, loop start, which we don't have yet. After the body, we call this function to emit a loop instruction. That instruction needs to know how far back to jump. Okay, so loop basically means jump backwards. When jumping forward, we had to emit the instruction in 2 stages since we didn't know how far we were going to jump until after we emitted the jump instruction. We don't have that problem now. We have already compiled the point in code that we want to jump back to. It's right before the condition expression. All we need to do is capture that location as we compile it. And I've already forgotten what I called it. Loop start equals self chunk. Like get offset or something. Chunk. Get line. Get constant. Get jump offset. Okay. Oh no, it's not get jump offset. Lines length. Count. Yeah, it's just count. Just like here. I tried to keep it simple for myself, and then I got all confused. So after executing the body of a while loop, we jump all the way back to before the condition. That way we reevaluate the condition expression on each iteration. We store the chunk's current instruction count in loop start to record the offset of the byte code right before the condition expression we're about to compile. Then we pass that to a helper function. Okay, so here's emit loop, and it's right after emit bytes. Emit loop, not self. And this is going to be a little crazy because we're subtracting loop start from the current count. +2. That should be okay. should be okay. Self emit byte opcode. We've got a new opcode loop. And then we're going to say let offset is equal to self.chunk.count minus loop start plus 2. You know what? Well, I'm going to add the 2 first before we subtract the loop start in case it ends up going a little on the negative side. It shouldn't, right? If offset is greater than U16 max as usize. Oops, it should be max usize. Self error loop body too large. And then we say emit byte. How did I do it before? I just want to see because I shifted by 8. Oh, I just did it this way. Okay. This is offset shifted 8. XF as U8. And then self emit byte offset and OXFF as U8. That's it. All right, so that's emit loop translated into Rust. It's a bit like emit jump and patch jump combined. It emits a new loop instruction which unconditionally jumps backwards by a given offset. Like the jump instructions, after that we have a 16-bit operand. We calculate the offset from the instruction we're currently at to the loop start point that we want to jump back to. The +2 is to take into account of the size of the op loop instruction's own operands, which we also need to jump over. From the VM's perspective, there's really no semantic difference between op loop and op jump. Both just add an offset to the IP. We could have used a single instruction for both and given it a signed offset operand, but I figured it was a little easier to sidestep the annoying bit twiddling required to manually pack a signed 16-bit integer into 2 bytes. Sorry, and we've got the opcode space available, so why not use it? For some reason I thought I could get through that in one breath and I couldn't. Okay, so we do need to create this op loop. It's just called loop. Here is the, right before I do that, I needed to 23 opcode loop. This should be into to convert it into the U8 properly. And then down here, opcode loop is going to be, it's also a jump instruction, but with -1. So we're gonna put false in there. Self jump instruction. Actually, I should do this in a smarter way, in a more rusty way. Enu jump style. Forwards, backwards. That's better. And then here, you say use jump style. And then down here, we say forwards. And then this one is op loop backwards. Offset. That's much easier to read. Okay, and then down here, instead of forward jump, this is going to be jump style. And then we can just say a forward jump is jump style forward. Right? Oh, I was just scanning that and I noticed I got a lowercase p there. Okay. And that didn't work because use jump style. I thought I could throw that in there. I thought I could throw that in there. Can I put it in here? Oh, And of course, they need to be comparable. Loop is not covered. Didn't I just... Oh, yeah. Loop is not covered. Okay. Opcode loop. Okay, let's write that. So we read the short. Let offset is self-read short. Self IP minus equals offset. Done. Yeah, there we go. That's our while statement. It contains two jumps, a conditional forward one to escape the loop when the condition is not met, and an unconditional loop backward after we've executed the body. The flow looks like this. Okay, so we should actually have now while loops. I'm afraid to run it because if I have a bug, it's going to do an infinite whatever. So if I say while, I can say var a equals 0. While a is less than 5, print a equals a plus 1. This should work. I think it did. So we get the global a. We get the constant 5. We check for less than. If it's false, if it's not less than, then we'll go to 23, which pops and returns. If it's true, we'll pop the result of the condition. We'll get the global a again onto the stack, and we'll print it. We'll get the global a again onto the stack, add the constant 1 to the stack, add the two values, set the global value, and then pop. What's this pop for? And loop goes from 20 back to 0. And then we pop again. Oh, this unconditionally. So what's the extra being popped? Is that the condition? Jump if false. No, we pop the condition here. We do the work. And we pop again. Let's take a look at it executing. So we get the global a, we get the constant 5, we compare. Is it false? It's true. So we're going to pop, we're going to get the global, we're going to print, there's the print. We get it again, we get the 1, we add, we set the global to 3, then we're going to pop. Oh, set global doesn't pop the value off the stack? Apparently not. I've forgotten that. Let me take a look at set global again. Yeah, it just does a peek. Okay. Okay. And here's where it finally ends, right? So here's the top of the loop for the last loop. Right, this is the last loop right here. It gets a global a, checks it, compares it to 5. It's still less than 5. So we're going to pop the result, get the global, print it, add 1, and then loop. And then the final part is we get the global, we see is it less, it's false. Jump it false to 23. 23 pops the false condition and returns. Neat. So while loops are really easy. There wasn't a lot of code change here. This I did because I was being a little stickler for coding style. Why have a bool when you can actually say what it is? And this actually could be cleaned up a bit too, but that's all right. And that's our loop, which is the jump backwards. There's the while. That's the whole while statement there, and we're done. Clippy's happy. Section 23.3 while loops. I think it's 23.3. It's a very short. Yeah, 23.3. Okay, so four statements. And I think what we're going to do is, because I'm running low on time, this is 4 statement stuff, as I remember from the JLox version. Yeah, this is a little complicated. I'm going to save this for tomorrow, and then we can take a look at the challenges, and then read over the design note considering go-to harmful. I remember Dijkstra wrote go-to's. Yeah, here it is. Dijkstra wrote this go-to statement considered harmful. back in 1968, back in the before times. Okay, so let's do that. Let's wrap it up here. We have 4 statements for tomorrow. I don't like the way that goes right to the top there. Okay, git push. Let's take a look at the changes. Yeah, so this is what we did. We did if statements, we did else clauses, we did logical and, logical or, and we finished while loops. So for tomorrow, we're going to work on 4 statements. Or am I? There was something else I wanted to do, and that was back here and work some more on this. Let's spend a little time on this. This is the JLox thing running all the tests, and our first failed test is over here. So let me just spend a little time doing that, and then I'll call it a stream. And then tomorrow we can work on 4 statements. Okay, so what were we doing? For our too many arguments, this is what's failing, right? So the way we check it is we run our code. And see what this is the output. And then we run we have to run the reference version of the code to compare to see what the output is supposed to look like, and then can make our code conform to the code that is expected. So let's take a look at what this test. Oh, that was a mistake, wasn't it? The error should be error at A can't have more than 255 arguments, and we're seeing error at A can't have more than 255 arguments, but we're also getting this, which means that this is not aborting. And I think it needs to abort. Let me see, is there a Java? Yeah, so I can do this. Oops. Let me grab that again. There we go. And so this is what. Oh. Maybe I have to do this. I should write a little test runner. Yeah, okay, so the only error we're getting is this, and what's error code is 65. Okay, so this needs to abort immediately. Can't have more than 255 arguments. We can fix that. Git status. What are we at? We are clean. Okay. Have more than. Ooh, there's 2 different places. Oh, one's parameters, the other one's arguments. Okay. So line 451 is this should return. And it's been a while since I looked at this code, so I've forgotten what this looks like. Error. It does return a locks result. So if I just change this to return statement, it doesn't like that. Oh, error, like this. There we go. So if we do that, oh, I have to build it. Like that, and then come back up here and take a look at this, and now it says that with the same error. Okay, so now let's do our Dart test. All right, so we got down to 78 now. Oh, right. So here's the first output thing that's not related. Okay, we're 178 and 61 now. Okay. So expected output fn foo on line 2 and got function foo. So this was just a difference between the way I was doing output, which we can fix. That's easy enough. Git add. Oops, I meant to do cargo clippy. Fix error message for too many arguments. Okay, so let's take a look at this one. RG function. It's going to be all over the place, right? But where's the output for it? Here, right here, in locks function. Right, so it just should look like oh, here it is, display. Okay, let's get rid of that, and this should just be fn, and we're going to ignore the parameter list. I guess we don't have the param list anymore, right? If we don't need it, we can get rid of this whole thing. Boom. And then expected output native fn and got native function. Is that in here? Nope. That's here. Oh, that's in debug. That's fine. Native fn. Okay, so let's see if that gets us to pass test 78. It does. Look at that. Okay, so let's fix. Let's commit that. Git add source. Git commit make function name and native function name output conform to reference implementation. All right. Expected runtime error, only instances have fields, and got only instances have field. Ooh, this might be just a missing period. Only instance. And instance that have properties, same thing, right? Okay, that should pass 82. I mean, sorry, it should pass set on nil and get on string. Oh, and this is another one. Can only call functions and classes. This would be great if I can get this whole thing just to pass. Only call functions and classes. What about this one? Error at quote quote expected property name after dot. Error at end. Ah. Now this is going to be trickier to fix because okay, let's get this. What are we at? 192 versus passing and 47 failing. And this, maybe we can clean these up because I think that other error message is going to be a little trickier because of the way I designed the thing. 198 and 41. Yeah, this one, let me save that one. Unexpected output, illegal expression, unexpected output, missing expected output. Oh. Uh-oh. This might be a little more complicated too, because it looks like we're checking equality. Oh, and I betcha my version of the code doesn't allow for, yeah, line 7. 1, 2, 3, 4, 5, 6, 7. It doesn't allow comparing Booleans with numbers, right? My illegal expression. Here's what you can compare. You can compare two numbers. You can compare a number and a string and a number, a string and a string, a bool and a bool, a nil and a nil, or nil with anything. But I don't have bool with number or bool with string. That's going to make this explode in terms of combinatorial complexity. It'd be nice to be able to say either way, but okay. Let's go back and take a look. I just want to see if I can fix up the easy ones. Oh, we're missing that. Okay, that doesn't look like an easy one. Oh, okay. This one's straightforward. Is it in Locke's class? Yeah. Yeah, because I'm printing out everything. I'm just dumping the whole thing. Maybe that needs to be debug output instead of display output. And then we'll say import format display for Locke's class. And just say write. Oops. Let's just grab this because it's the same thing. Bang F, and it's just the name of the class. Self name. One thing that's missing from Rust right now is to be able to put self.name in here. Hopefully that's coming soon. Oh, okay. I'm not going to do that then. Expected enum result. Oh, because I put a like a fool. Okay. Expected output B, expected output foo. Okay, so these ones will be easy to fix. And then we have outer instance and got instance of class outer. So that's instance, right? Instance of. Yeah, so this should just be, and we don't need fields and anything like that. We just say write F outer instance in lowercase, and this is self class. Right, so that fixes that. 40. This might be, yeah, illegal expression, so this is probably something similar to what we were seeing before. That we saw already. Operands must be 2 numbers or 2 strings, and got illegal expression. So that we're going to have to fix as well. Operands must be numbers. Okay, so that's all related to all of those. And those. Okay, so we went 198.41. Let's build this and see what we get down to. Two, 9, and 30. Okay, so we have 30 tests still, and I think most of it is going to be this business here. Where when we're checking comparison, source interpreter, where is it? Here. Yeah, and I just basically ignore all of that stuff. So I think what I'm going to want to do is simplify or refactor all of this in order to fix all the remaining 30 errors. I think those are the only ones that are left now, are the ones related to the binary operators. Oh, and this one, right? We have to figure out how to get the end there. And this one's weird. Oh, look at that. We should be seeing this. Okay, so let's take a look at what do I show for it. Oh, it's supposed to barrel on through. It's supposed to just keep going. I see. For expect expression. And I'm returning an error, but it sounds like maybe we should just return OK. Well, we shouldn't return OK. We should flag that an error occurred. Right? Although I wonder what it's going to break. Okay, let me clippy this. Let me commit this. Git add source, git commit, clean up output, do conform. And then let me just change that expect expression. So instead of doing this, what we'll do is we'll just call self error peak expect expression. And return OK. And that might break everything. Oh, we do need to return. Yeah, if we're going to keep going, we can't. We can't return OK of nothing. We have to return an OK of something, and it has to be an expr. Is there some really cheap expr we can? I'm trying to look. I don't see any really easy exprs. I guess we can just throw back a false. There. But that's probably going to break everything else, which is why I did it as a separate thing. Okay, let's build this. And see what it does. Okay, so now we are getting this, but instead of saying expect semicolon after expression, we're saying expect semicolon after value, and we're doing this again. Oh, we need to advance. We need to advance past the thing. So not just peak, but okay, and I'm out of time, unfortunately. We need to, yeah, not just peak, we have to consume it. We have to advance. Self-advance. I guess we could do that. And see if that helps. Oh, maybe we have to synchronize. Maybe that's what needs to happen. Yeah. Maybe that's what I missed. Expect expression. Synchronize. Yeah, we just have to call synchronize. Like that. Let's see if that does the trick. Almost. We synchronized up to the A and then it failed. So, okay, we're going to have to take a look at that one. That's going to be a little bizarre. And I wonder how many other things are failing now. Yeah, now we have 45 tests failing because I changed this. Okay, I'm going to check out this. Git push. And that is what? Ooh, not Twitch search. Let's take a look at my repos here. There we go. LoxAST. Okay. Yeah, so we did a little bit of cleanup today, but not much. And then we got to figure out what's going on here. Let's get this back to working. Only 30 failures. Only 30 failures. Yeah. Okay, so that's where we'll leave it for today. And let's call it a stream. All right, thanks everyone for hanging out with me. And I will see you tomorrow where we're going to look at four statements, sorry. And then read over Bob's write-up on, or Bob's take on the go-to considered harmful. So that should be fun. All right, have a great rest of your day, and I will see you then. Take care.
I don't know what y'all think, but I think that's pretty.